So please welcome Ingrid Epure.
Hi, everyone. I'm very thankful that you're all still here, or part of you are still here. I know that we're only like an hour away from the party. I'm also very thankful for this podium that for the first time in my life, it actually fits me. So, because at the beginning of every talk, there's always a little bit of a technical difficulty. There we go. Now we can start. So hi, my name is Ingrid. I'm Ingrid E on Twitter and GitHub and a bunch of other internet places. So I usually start my talks by just telling you a little bit about myself, which is more of a confession than an actual profile. I'm obviously a very serious person, a very serious engineer, as you can tell from my photo with Jim Bennett from yesterday, just hanging out before DEVit. And I have a very, very strong dislike for things that are unnecessarily complex. And by complexity, I mean application complexity, architecture complexity, code complexity, which are things that, as engineers, we encounter very often in our day-to-day job. So much that I've put all this rage last year into a bunch of talks where I point out that as engineers, our jobs would be so much easier and our lives would be so much easier if we would have the right tools to be able to support our jobs. And areas that we've never worked in before, like security in my case, would become so much more accessible to us all if we would have the right tools and the right support and if we would just talk to each other a little bit more. So in a way, the talk today is going to follow that. And it's also going to follow a little bit of a tour that I did in the last 2 years in my previous job, from joining a front-end team to an operational team, and then back to back-end, which is my initial experience, I guess, or my original background. And I love this 360 team, and this is actually my first ever 360 conference, yay! And it's great to be here because I love the idea of sharing, and I love the idea of talking to each other, and I think we should talk to each other a little bit more. And notoriously and traditionally, tech hasn't necessarily been very good at that. I feel like we have a lot of silos where if you're a front-end engineer working on a front-end team, you would say, I'm a front-end engineer, I build awesome user experiences, and that's awesome. And then if you're a back-end engineer, you'd say, well, I'm a back-end engineer, I build highly scalable, highly available services, yay! And then if you're an operational engineer, production engineer, or SRE, whatever you want to call yourself, depending on the company that you work for, you kind of rant on everyone for like breaking things and kind of go, stop breaking things. But also, as your main responsibility is to keep the app running and available and actually build on top of everyone else's work and add to it and make it even better. And that's been working for many, many years. It still works today. A lot of companies, the way they organize their teams is exactly that, front and back end operations, design. I've heard something about design ops earlier that would fall under this category as well. And it's been working, but the problem with it is that at the same time, it creates a lot of fear. We've probably all known a little bit about imposter syndrome. It's notorious in our industry. And when I say fear, I mean a bunch of different things. It can create fear to make changes. You get a little paranoid. You kind of feel like, ooh, I'm stepping outside of my comfort zone. I'm not really in the UI-friendly, cozy environment that I've been used to for so many years. Now I have to look at a database. Ooh, scary. Or you're afraid to fail, because obviously when you have less expertise, you feel a little unease, right? Kind of like traveling. You're in a new country. You don't know what the hell is going on. You don't speak the language. Holy shit. You can be afraid to cause an outage, which when I joined the production team, that was exactly my main fear. I've never caused an outage before. I now have. I've gotten my stripes. But I was really afraid of that. And the reason why a lot of people are afraid of it is because we're not really making it that safe to fail or feel okay with the idea of causing an outage. I mean, across the industry. Some people are better than others. But you can also be very afraid to have a different opinion. Imagine that your background is X, and then you join a team that has a completely different profile. And all of a sudden, you find yourself in this room with people that have been doing that for years, right? And you kind of go, I don't know if I agree with that. And then you kind of feel a little bit weird. And depending on your experience, it gets better with time. If you've been around for years, you kind of speak up and go, hey. But it does happen at some point to feel very uncomfortable. And that's a little sad. And I guess there's many causes for that, besides humans being, well, humans. We've added a lot of complexity over time to our applications, like hello, Elasticsearch. It's not very nice to run Elasticsearch. Hello, containers. You've probably seen that one, MongoDB. I'm not going to continue on it. But it's also because the lack of proper developer tools. We're still pretty new in the area. Developer tools is still a somewhat new concept, which is a shame. And the lack of developer tools are increasingly make it slower and more painful for us to, or not necessarily helping with us doing our jobs a little easier and a little more human and a little more being okay and more comfortable with the idea of failure and being able to mitigate failure. Imagine that, I'm pretty sure there's still companies. Raise your hand if you still have manual deployments. Yeah, there's a few of you. Raise your hand if you still rely on an ops team to deploy your changes. A little bit? Okay, cool. So imagine being in the middle, I don't know, MySQL crapped itself, because it happens, even boring technology has faults, right? And then you have to deploy a change or make changes to make your customers less sad and less pinging you on Twitter going, what the hell, you're down. And then you don't have the right tools to deploy your change fast. It's kind of sad. It adds a lot of unnecessary pain. So if we were to draw the line and look at all these different teams, each with its own mission and with its own description, we kind of all want the same thing. We want to be able to understand the impact that our change has in production. But more importantly, we want to be able to support and champion the awesome feature that we just deployed and we've worked weeks, months, days. And being able to jump on board and help when something has gone poorly, because it does happen, and figure it out is one of the best feelings in the world. You've probably had that. It's one of the reasons why I absolutely love my job, that you start with having absolutely no idea what happened, and then as you keep going, you gain more and more clarity. And a lot of people talk about debugging and tracing with the idea that it's an art, right? Like you just can't do it like off the book. It's just something that it takes experience and years in practice, and it's just magical and amazing. And it actually shouldn't be. If you have the right tools to allow yourself a degree of creativity and being able to ask questions and get answers from your systems, from your tools, it wouldn't actually be that magical, mystical thing. It would actually be something quite normal. And then instead of being an art, it would just be you recognizing patterns over time as you've gained more and more experience. And that's pretty cool, right? It's kind of like a more human outlook on it. So let's talk a little bit about the impact. Let's say that as a product engineer, you want to build a list that displays articles. And then you want to be able to filter by the state in which your articles are and just display that to the customers. So we're going to assume that you've worked with a designer and everything is approved and like everyone's happy with the design and it goes to production, and you have a bunch of tools that are going to help you get there. It's a little out of the scope of this talk, so we're just going to assume they exist and go back to that a little bit later. After your changes in production, now the customer is ready to look at it, right, and start using it. So if we were to look at different components that goes into a customer opening a list of articles, it would probably look something like this. You have a browser, and then you have a DNS. We're going to talk about DNS a little bit later, which is a lot of people are afraid of DNS. I'm hoping that by the end of this talk, you'll be less afraid of it. And then there's a way in which the browser manages to automatically talk to the backend. And then you have a service that does a bunch of logic, and you obviously have that data stored somewhere. So let's try and break it down and see if it's really that scary. From the browser's point of view, when you just type your address, its main mission is to try to understand what the hell are you trying to do. So the way browsers do that, it's by splitting the address that you just typed in the address bar according to a pattern. And that pattern is the protocol, the host, the protocol, and then the host. And then you have a port, that's optional. And then you have your path to a resource, and then you have a query. So if we were to look at the address that we had earlier for our article list, the protocol in this case would be HTTPS, because we want to be secure. And then myapp.com would be the host. The port would be 443, which is actually unnecessary in this case because the default port for HTTPS is 443. And then you have your path to the resources, which is articles list all. Pretty cool. The next thing that the browser does, it looks at your host, which is where your resources are located, and it goes, well, I don't know what this app.myapp.com is. I have no idea. So it has to find out. And that's what, in simpler words, that's where DNS comes to play. And historically, the way we've done that up until 1980 was to have a host.txt file locally. And actually, funnily enough, Windows still does that. There's still a host.txt file on your OS. If you use Windows, it's on each of your laptops. And in 1983, the internet was exploding, and people realized that that's not going to scale that much longer. So they wrote the DNS, which is a service that its main job is to resolve an address, app.myapp.com, to an IP. So let's go through that process. The idea of checking things locally first, because local is faster, it still exists. So the first thing that the browser is going to do is going to look at its own cache and see if it has any sort of memory of app.myapp.com. If it doesn't, it's going to go to the OS, see if the OS knows anything about it. And then if not, it's going to go to your router. And then if the router fails to answer, to your local DNS, which is usually actually the internet service provider's DNS. And if all that fails and there's no cache record, it needs to actually make a request to a DNS server, which is done via UDP. There's a lot of recursion and a lot of caching in DNS, so all these layers come with caching in an attempt to return the response as fast as possible. So it goes like this. It goes to your internet service provider DNS, and it asks the same question: have you ever seen this address? And then if it hasn't, it's going to go to the root name server, which is kind of like the authoritative for that area. The source of truth for that area is the best way that you can look at it. And that's going to redirect the top-level domain name servers. So the way DNS works is that it's going to read your address backwards from .com to my app to then app. So it's going to go and it's going to ask the top domain name server, hey, do you know anything about .com? And then they're going to go, well, here's the address and here's where you need to go. And from there, it's going to go to these authoritative name servers, and they have the information about what myapp.com actually means. And from there, you can actually go to the DNS record itself, which is app.myapp.com, which is exactly what we need. And depending on what we're trying to do, it's going to respond with either a CNAME, which is like a reference to yet another record, and then this whole cycle continues. Or it's going to respond with an address record, which is an IP and a time to live, which is, yay, exactly what we want. So the browser doesn't care about addresses, it cares about IPs. And until it gets the IP, it's going to go through that loop over and over and over again. But once it has the IP, it's pretty happy. It goes, yay, I have my IP. I know what this is. And it's also, like, on the way back, it's going to update all the caching so that next time that it asks, it's going to be much faster. Pretty clever, right? The thing about DNS and all these lookups and the time to live is that it can actually have an impact on performance. And this is the reason why engineers should care a little bit about it. Each record has a TTL. And obviously, the lower the TTL, the faster it's going to expire from the cache, which means that the server is going to have to go and do all this lookup every time, which is going to impact the performance. We're talking milliseconds, but sometimes that actually matters. A higher TTL, however, means it's harder to make changes. So if you have a TTL set to, I think, 300 milliseconds, it's going to take like 300 or 500 milliseconds for that change to actually propagate. So if you want to change app.myapp.com to ingrid.myapp.com, it's going to take that long for you to actually see the change. So now the browser has the IP. It's like, okay, cool. I kind of know where to go, right? But it doesn't know what's on the other side. And it's kind of like two humans meeting. You recognize that the other person's a human, but you don't know if they're like a psychopath or they're a nice person. You kind of don't know. So it does what you would do. It waves at it. Kind of goes, hi, I am here. I want to talk to you. And that's done through, it's called a TCP three-way handshake. So the browser sends a request with a send signal to like, hi, I want to talk to you. And then if the server on the other side, which is usually a load balancer, is nice and it wants to talk back, I would send this in acknowledged. I've acknowledged your wave. I'm going to wave at you as well because I'm actually nice and you can talk to me. And once that's received, the browser is going to go, okay, I see that you're waving back. Now we're friends and now we can talk. The reason why it's really interesting is that there was a bug in AWS on one of their load balancers where the second layer, the SYN-awk, was actually broken. So a percent of our requests ended up being 5xx, which is a pain to debug. It was not nice. I think they fixed it, but it's kind of interesting why sometimes you can see errors on the client side without being actually the application's fault. So once you're friends, obviously you can finally send a request. And what I mean by a request is a classic HTTP GET request. Majority of websites, sadly, still use HTTP 1.1, which is a pretty old protocol. And again, in the beginning of time, when people didn't quite know what web is going to be and how big it's going to be, the browser was limited to 2 connections to a website, which, as you can imagine, it didn't go very well. It didn't go very far. And they had to change that. So they, instead of having 2 connections per each host, you were allowed 6. They picked 6. I'm not super sure how they picked 6, but there's a rumor has it that they didn't want to double it because they wouldn't think it would be enough. And if they go 3 times as much, it would give them a little bit of a breather. It obviously hasn't worked that well because HTTP 1.1 is essentially now seen as a hack. And a lot of people, Google very strongly pushes for HTTP 2.2. HTTP 2, sorry. And the advantage of HTTP 2 is that it allows for response multiplexing. So rather than having to do, imagine that you have to load multiple things on the page, so you have to do multiple trips to the server. HTTP 2 allows you to do that in one go, so it will keep the connection alive, and it will also allows for header field compression, so you can do, you have room to do way more things just by using the headers. That all sounds very complicated. There's actually the guys from Golang built this really cool demo where they took a picture of 2 golfers and they split it in 180 tiles. And then they allow you to compare how long it would take for you to see that photo on HTTP 2 versus HTTP 1. So the first picture is HTTP 2. I strongly suggest you go play with it. It's awesome. So the first picture is over HTTP 2, where it loads almost instantly. Obviously, depends on your internet connection, but it's fairly fast. The second one is where, like, how far it got while the first picture actually loaded. So the TLDR, and without going too much into the details because it would be a talk on its own, just switch. It cannot get worse than this. So just switch now to HTTP 2 and your app will thank you and it's going to be so much better. So we've successfully sent a request, hopefully over HTTP 2, so it's reasonably fast. Now we have to go and search for those articles and load those articles so that we have something to display. So what the service is going to do is send a request to a database. And we're going to try and focus on MySQL because it's probably the most known and I guess most used still. And what's really interesting about it is the way MySQL decides to execute your query. And the worst outages, or the outages that a lot of people fear most, are outages caused by bad queries. So I think it's useful to have a look and understand how MySQL executes a query. And it actually does it a little more simple than you might think. You've probably heard of a thing called explain, where you can run explain, literally type explain, and then your query, and then you're going to get a bunch of information back telling you what that query means for the database. Turns out that the MySQL server is actually using explain itself internally in the way it executes the query. So it's not just for the user information, it's something that it's dependent on. And there's a couple of fields that are really interesting. And the first one that I want to chat with you a little bit about is the possible keys, or the possible indexes to choose. So you might have heard this idea of indexes, and when you write a query, you should make sure that you hit an index. Well, what the hell is an index anyway? You can think of an index as a really good cab driver, where you'd give it an address, where you tell it what you want, and then it would take you there. So an index is kind of like that. It has awareness on the lines. It's basically a pointer to the lines on the table that are relevant, and then it's able to retrieve you that information very fast. Obviously, technology has advantages and disadvantages, so indexes are not free. They do take space, like physical space on the database. So the more indexes you have, the bigger the server needs to be. But also the more indexes you have, because a lot of people are going to be like, I'm just going to add indexes and then my performance is going to be awesome, is that it takes a cost on the read operations, like read, update, and delete. If you don't have a lot of those, then having more, you can probably get away with having more indexes and a bigger host. If you do, then that's not a very good idea, and you're not going to have a very nice time. So ideally, when we write a query, we should have or think of the indexes that would help make that query more efficient. And usually what you're aiming to do is that you want the columns that you select to be part of an index. What's really nice about it is that MySQL automatically adds the primary key. So you don't, after 5.6, I think. So you don't actually have to worry about the primary key if you've already had a big database and you've missed that. But ideally, when you write a query, you want to keep this in mind. Something really useful in the output of explain is the number of rows. So the number of rows is exactly how many rows are going to be examined before MySQL selects the ones that you need, and it's going to return the result. So say you have a 500,000 rows in a table. If your query is going to have to examine all of them, you're going to have a really bad time. And usually these two are connected, so the better the index, the more rows it's going to eliminate out of the query, so it's going to be faster. And the third thing is the extras. So very often we're very tempted to sort as well and return sorted information. For example, return the articles in the sorted by the created at, where you'd get the most recent ones first, obviously, and the older ones after. Again, depending on the number of rows, MySQL might decide that it needs to use file sort, or it needs to actually create a temporary table to be able to handle your query. The thing about file sort is that it's actually very poorly named, which is the reason why I like mentioning it, because I like ranting about it. It's actually implemented like a really basic sorting algorithm, which is quicksort, and then so it takes your set of data, it splits it into chunks, it sorts them using quicksort, and then it merges them using merge sort and returns them. And sometimes if it's running out of memory, when it's doing that, it's going to absolutely go to disk. But it's not necessary. So since naming is one of the hardest problems in computer science, I thought that this might be a cool thing to mention. But for those of you that like math, MySQL also wrote this formula where you can kind of estimate the number of disk lookups that it would take to be able to return your query. I won't go into too many details, but it exists, and their documentation is actually strangely good. So everything that I've learned today, I've learned from that. If you're more curious or use MySQL, I highly suggest you go read it. The thing about the database, and what I really want to mention, is that it doesn't only care about one request. You have one request, and it takes X amount of time, and if the query is really bad, that would absolutely have an impact on latency. But the database also cares about the number of requests. It cares about all of them. And the more requests you have, the more instability you could potentially induce in your server. For example, MySQL Aurora has a limit on 18,000 requests. If you get to about 16,000, which I've once seen, you're going to have a really bad afternoon. And it kind of makes sense. And in time, this is actually very prone to happen, where you want more users, you want your app to grow, right? Which is very exciting. You hire more machines to do work for those users, which results in more connections, which puts more pressure on the database, which is going to turn it to less of a database and more of a shitty database, and then you're going to have a really bad afternoon. And there's ways to work around that. When you're still at the beginning, you can add caching in front of it. So for the really hot paths, like, say, articles is a very frequent path, you can add caching, which is basically a key value store in front of the database to limit the number of times that you actually have to hit it to be able to return the information. Or you can look into something called connection pooling and multiplexing, which some languages like Java are a little bit better at. Rails, which is what I've spent my last 2 years, is not. So there's other alternatives, like for example, Proxy SQL, which acts as a proxy between your server and the database, and it has a clever way of reusing the connections. So you might have noticed that I've purposely kept out the backend. We've talked about the database, we've talked about how you get your request there, but we haven't really talked about the system itself. And the reason for that is because it could be one app and one server, or it could be an actual distributed systems that's behind or disguised as one server in the beginning. And that's harder to gain visibility on. And it's harder to predict ways in which it will fail. It's a really good paper. It keeps getting referenced in almost every distributed system talks. It's written by MIT. It's called How Complex Systems Fail. And it's a really good read. I strongly suggest you read it if you want to be very scared about the future and how we do software. But Charity Majors, which is the CEO of Honeycomb, which is a great product, makes a really good point that in time, given the complexity of our systems, the majority of our questions, or the questions that we kind of want to ask, or we would need to ask our server, tend towards the unknown unknowns, where we can't even predict the ways in which it's going to fail. Like, I can't even. How did this happen? I have no idea. And the only thing that we can do about it, there's no way in which we can accurately predict the ways in which a complex system is going to fail. But what we can do is build a system with resilience in mind, with trying to be as resistant to failure as possible and recover from failure in a nicer way, or cope with unexpected input in a more sane way. But also adding a lot of instrumentation so that we gain a lot of visibility into what happened and allow ourselves to go in and take time to understand why that happened. Something that's also very important is making it safe to deploy and roll back, making it very safe to make changes and actually take all that fear that, oh my God, what if I break something, even out of the conversation. So instead of treating failure like a really bad, scary thing, treat it as something normal and allow yourself allow yourself to be able to roll back and mitigate a change really, really fast, allowing the engineering team to take time to fully understand the problem. So are we doomed? Are we just going to be stuck into the unknown forever? Is there any way out of this? And it kind of is. You can't really predict failure, but you can observe, and you can see how your system behaves when something unknown happens. And this goes back to the idea of observability, which has circulated a lot has gained a lot of traction over the last 2 years. And the way I see the idea of being able to observe a system is that you have all this data, and you should be able to craft a story with all that data to help understand how your system behaves when it's facing unknowns. And those unknowns can be anything. It can be a failure in one of the components, it can be unexpected input, it can be, again, unknown, it can be anything. And to be able to achieve that, you need to obviously add a bunch of things that would be able to support you in this mission of gaining visibility. And they usually fall into 3 categories, which is tracing, logs and events, and metrics. So let's talk a little bit about that. Tracing is something that looks a little bit like what we've done up until now, where you're trying to explain a request lifecycle from the beginning all the way until your data actually gets returned from the server. So it's a deeper understanding into the request and execution, and it's also a great way to understand the control flow of your app. You can imagine that when you have maybe a 4-year-old application, which is also on a shared code base, it's a little hard to see all the methods and all the parts of the code that are going to be touched by a particular request. So tracing is actually a really good way to gain more visibility into that. In fancier terms, it allows you to be able to ask your code or your system a few very useful questions like, what's the high-level structure of the code? Wouldn't that be nice? Remember that first day when you start your job at a company and then you have to do, like you have your first task for the week, and if you're lucky, it's like on a smaller server, but small service, but very often it's not. It's a ginormous piece of code and you don't even know where to start because it's very poorly documented. This really helps. Or I want to be very performant. Where is it that I'm spending most of my time in? What's going on? Is it the database? If it's not the database, where the hell is it? How many calls to a service or database is this triggering? I'm trying to load articles. Why am I seeing a query increase all of a sudden on my database? What's going on? And also, do I have any instrumentation gaps? Is there anything unexpected in the timeline or in the duration of this request that I have no idea where it came from? And there's a couple of vendors in this area, where like software as service, but it looks pretty much like this. So it's a little hard to see, but basically it accounts for every method, so every hoop that your request has to jump in before it returns the result, and it's going to give you the duration of each part, which is pretty cool, and if there's an error, you're going to be able to see it. Open tracing have been in this area a little bit longer. Honeycomb are a little newer to tracing, and they've been fighting very hard for this to actually be a standard. But they're both really cool to have a look at. They have really great documentation on this if you want to check it out a little further. But tracing itself, as great as it is, and as much visibility as it helps you gain on your code base, won't have all the answers. It's lacking a little bit of context. Where did that request actually come from? What triggered it? What's going on? So logs or events are a nice addition to that, I guess. And when I say logs, there's usually a little bit of a philosophical debate around logs, where a lot of people would treat logs and events differently, or would argue that a log is also an event, or that we should use one over the other. I guess for the purpose of this talk, when I say logs, what I mean is that it's a written record of an event that happened in your app. And a log is basically a source that knows absolutely everything. What happened at X time on this server. Because of that, and because the outreach of it, logs are great in many different use cases, from analytics to security. Security teams usually rely on this very, very heavily to understand when someone is doing something that they maybe shouldn't, so that they can block it. And because of that broad reach of logs, it's a non-trivial. We haven't quite figured out in so many years how to do logs quite right. So it's a little bit of a journey. We're in the beginning, and I'm pretty sure there might be some of you in the audience that are still in this time. Logs were a mix of text and a lot of other information. For example, this is an example of a Rails application log where it's everything. It's a mix of key value stores separated. Key values are separated by space, and then because you also want to log parameters, because why not? More data is cool, right? Parameters are actually logged in JSON, so it's a mix of space-separated values in JSON. Ain't that lovely? The problem with this is that grep can only do so many, and searching string can only do so many, and it's 2018, it's time to structure our logs. This is not 1998 anymore. It's not cute to have text in your logs anymore. So the first thing that a lot of people have been doing is putting structure to logs, and the most common used structure is JSON, that allows you to have a little more control on the data that your logs have, and also provide or support an easier way to be able to search those logs. But just by adding structure around it, it won't help you answer questions like, how many requests per second is this user making to my stack via this endpoint? I don't know. How many 4xx requests has this app been making over the last 24 hours on this stack? We don't know. These are all high cardinality questions that is very hard to answer without proper context. And turns out that this exact context is called canonical logging. It's a concept that has been around for a while. There's actually a really good blog post by Brander about it. And it's this idea that you can add a set of fields to your log that describe the environment of a request. And it's a little bit of a middle ground between how effective a metric is that just tells you the answer very fast and the details of log traces. And it doesn't look scary at all either. All you have to do is just add an admin ID, a cluster, a host, a release, so that if something bad happens, you can actually see what was the release SHA that caused that problem. A timestamp, the user agent, because some browsers are horrible, so when your customers are complaining that this doesn't look that great, or they have problems on a particular browser, you actually can see why and what's going on, and if it's an isolated scenario or not. So now you have a better way of classifying your data, where you can say, well, how many 400 requests did I get from this person? There they are, and you can actually dive a little deeper and see where and what endpoint that hit, which is pretty cool. So the context and structure in logs helps crafting a story, where you're suddenly able to answer a variety of questions, and you also have support for high cardinality questions, like breaking down by app or breaking down by user, which is something that's very hard to do with everything else, with something else. So now you're going to think, sure, but this is a lot of work. Can we just use metrics? Like, metrics have been around for a while. Like, are you crazy? Like, why would I go through all this work? And the answer is not really. Metrics are historically easier to work with, and they provide answers to questions very fast. How many requests do I have? X. What's the average latency of my request on this API? Y. And it's very, very easy to measure the impact very, very fast, and very easy to get averages and aggregates out of those values, which fit scenarios like latencies, or when you want to be able to alert on something. My request count has suddenly gone to 0. I should probably fire an alert. My request count to the database is now 18,000. I'm going to have a bad time. I should probably call a human. And metrics are very easy to use because historically disk has been expensive, and people were afraid to do logs or use logs because disk was expensive. But disk is not expensive anymore. But people got and are still very excited by how easy to use metrics are, to the point where they create thousands and thousands and thousands of metrics. And the most common use case is, well, I've just deployed this change, and I want to measure the customer impact. I want to see, is this actually used? Do humans actually look at it? And the way a lot of us have been doing it is by just adding a metric, creating a dashboard, and then I'll just add, I don't want to wake up a human in the middle of the night, but I can create a Slack alert. So what ended up happening, actually, at a company that I used to work for, is that we had 8 times more dashboards than people. There were about 900-something dashboards and about 100 and something of us, so that was fun. And because of all this metrics fatigue, what starts with curiosity and like a really nice thing ends up being a disaster because your Slack is filled with notifications and you definitely don't want to look at it anymore. And then metrics don't quite tell you how you're supposed to feel. You know, you create a dashboard out of it, and if you look at the first example, which is the CPU utilization, I don't know how I feel. Is that good? Should I be worried? I don't know. There's no threshold there. So for a dashboard to actually be useful, it shouldn't make me think. I should be able to understand just by looking at it what's going on. So thresholds are something that are very, if you're going to create a dashboard, at least have a threshold for it, because numbers are not very chatty, and you can draw a line so a human doesn't have to think very hard before making a decision. So if it's all this noisy, what should I add metrics for? And there's, I think Tom Wilke Wilkie, I hope I pronounced his name right, came up with this system called RED. And he says that the metrics that you really need to care about is the request rate, error rate, and latency. Request rate, error rate, and latency, or the duration of requests. That's it. No more. Or, in simpler terms, and what operations taught me over the last 2 years, am I willing to get out of bed for this? Am I willing to be paged? Better be important. There better be coffee as well. So why all of this? This has been a pretty lengthy journey. Why all of this? It's not so that we would know everything, because that's impossible, obviously. It's not going to help us predict more failures, but it's going to help us ask questions at the right time. And hopefully, once this idea gains more and more traction, the tooling is going to eventually catch up with it. But it also moves supporting your system from the development and the testing stages into a real environment, into production, which is something that a lot of people are pretty afraid of or reluctant to do. And also because noise is really bad, and we want our brains to be free to be able to be creative, and too much data and too much noise and too many tools and too many things work against us in the end. And raw data is just noise, so we need data with purpose to be able to turn it into information that's actually actionable by the engineers. And ideally, we want to create change. Our tools haven't necessarily gotten better. It's still shit to run an elk stack to be able to move logging in-house. For those of you that decided to do that for GDPR, I feel sorry for you. I've been there as well. It's not nice. It's still shit to be able to have a proper logging platform in-house. It shouldn't be. It should be a little bit easier. We're still doing metrics like it's 1998. A lot of us still do logging like it's 1998. We need to be able to create change and advance. And companies like Honeycomb have been pushing and have been doing a really good job in the observability side of things, but it's just the beginning. We need more chats. And also we need to empower each other by talking to each other, by understanding that we're all in this together and we're all striving towards the same goal. So thank you very much. And I hope we can grab a drink together later.